Friends, welcome to this lecture 45 on advanced steel design. We are now continuing to discuss the derivation for finding out stresses on curved beams under large initial curvature. So, we are looking for curved beams with large curvature. Okay. So, we discussed the derivation for finding out stresses at the intradas and extradas of the curved beam for small initial curvature, and we also said very clearly that the stress distribution along the depth of the section in curved beams is nonlinear. The stress distribution across the cross section of a curved beam is nonlinear. Therefore, the classical bending equation cannot be used to find out the stresses. Okay? So, we need to really derive the control expression for finding out the stresses in the extradas and intradas, that is the maximum tension and maximum compression on the concave and convex side respectively. Okay? So, this was the discussion what we had in the last lecture. I urge that you should please redraw this figure again. I will hold the screen for a second. So, we have got the condition for a large initial curvature. Please remember that the moment is applied at the ends in such a manner that it tends to decrease the cross section. Okay? So, the convex side and concave side are marked on the screen, which is also called as extradas and intradas, and we have marked the neutral plane with an offset from the x axis by the amount E, which is indicating a shift of neutral plane towards the center of curvature. This is a very important statement, friends. Okay. This is moving towards the center of curvature by an amount E. Okay. We pick up a fiber at a distance y measured from the x axis, which is away from the center of curvature, and we mark that fiber as PQ. So, the figure 2 shows the cross section of the member, any arbitrary shape, where the extradas and intradas are marked as Ri and Ro on the screen. R stands for the radius and O stands for extradas or outer end. I stands for intradas or the inner end. Whereas the XX plane is measured at a distance R from the radius, from the center of rotation OO. Please understand, XX axis is different from the neutral axis. It cannot be same because XX the centroidal axis. Okay, XX is the centroidal axis and NN is the neutral axis. They cannot be same for a simple reason: the stress distribution along the depth is nonlinear. Okay, so it is not going to be same. In that case, there is no coincidence of this, and this shift is indicated as E in the figure. Okay. Now, there is a specific way by which we assume M. M is closing the curvature, right. Please understand, these are all standard conventions which has a positive convention in the analysis. Okay. We pick up any point y on the fiber PQ, which is offset measured from the centroidal axis. It is nothing to do with the neutral axis. Okay, I am always measuring the point respect to the geometry. Neutral axis is a layer or a plane respect to the stress distribution. There are two different things here. We have to be very clear about that. Okay. From the geometry, the section depth is marked from the central axis as HI and HO, that is height or depth of the intradars from the central axis and extradars from the central axis. It can be equal, may not be equal, depending upon the location of CG, because the sections can have also an asymmetric cross sections. Okay. Now, having said this, we will say let the curved beam has a large initial curvature. The radius of curvature is indicated as R. In the figure, where m the applied moment tends to decrease the curvature. Okay. So, friends, in curved beams there is no hogging and sagging bending moments. You got to classify the applied moment in terms of does it increase or decrease the initial curvature of the curved beam. Okay. So, very important, please remember this. Okay. Therefore, friends, M causes tension in the extradars, is it not? And of course, compression in the intradars. Now, let us consider an element ABCD. Okay. We will consider an element ABCD. We are considering an element A, B, C, D. So, let us consider an element A, B, C, D subtending an angle d phi at the center of curvature. Please see this figure. The member or the segment ABCD is making an angle d phi. Okay. Now, under the action of M, this element deforms. Is it not? This element will deform now, because the radius is going to change. Obviously, this element will deform. Let us now draw the deformed shape of this. So, let me draw the element. We call this as A, this as C, that is what we have, is it not? Yeah. And let us call this as B and D. This is my element. Okay. Let me also mark PQ. So, PQ was in cyan color, let us mark PQ. This is PQ. Now, let us mark the centroidal axis, which is in orange color. I call this XX. This is a centroidal axis, and we know that the element PQ is at a distance y from the centroidal axis, is it not? Let us mark that. This is y, away from the center of curvature. Now, let us also mark the neutral axis, which is in green color. So, this is my neutral axis, and we know this is at a distance E shifted towards the center of curvature. Okay. Now, under the applied moment M, which is tending to close the curvature or decrease the curvature, the element is going to deform. Let us draw the deformed condition of this element. So, what we do is ABCD is deforming, we will not disturb one face, we will just disturb only the other face for a simplicity. Okay. Let us mark that. So, at the neutral axis, there is no change, and let us say it is going to deform. We call this point as C dash and this point at D dash. So, Q will also get extended to Q dash. Sorry. Okay. So, we call this angle as delta d phi. Okay. So, now D is shifted to D dash, and let us note neutral axis is shifted towards the center of curvature. That is an important observation which we need to understand. Okay, it is shifting towards the center of curvature. Okay. Now, with reference to this figure, for our convenience, face AB is fixed. That is, this face is fixed. Face CD is rotated. And to C dash D dash, as you can see in this figure, you can see here, this is what you have rotated. is what we have rotated. Okay. Now, this new face C dash D dash is subtending an angle del d phi, sorry, delta d phi as marked. Okay, I mark this angle. Okay. Now I can say the new deformed shape is A, B, C dash, D dash. I think this is okay. There is no confusion in that. Okay. Now let us consider a fiber PQ at a distance y from the x axis. At a distance y from the x axis marked away from the center of curvature as shown in the figure. The initial length of this fiber will be r plus y of d phi, call the equation number 1. Now, when m is applied, the length of the fiber changes. To PQ dash, you can see here, this has become PQ dash. This has become PQ dash. Q has moved to Q dash. So, the new length of the fiber or increase in length of the fiber which is the consequence of the applied moment m is given by y plus E d phi equation 2, which I call as Q Q dash. From the geometry, can I say Q Q dash is y plus E of delta d phi? Okay. Having said this, let E be the distance of neutral axis from the centroidal axis Please note centroidal axis, neutral axis is moving towards the center of curvature. You may ask me a question, how this has happened, why it cannot move away from the curvature? Very interesting. Since M is applied such that it tends to decrease the curvature, neutral axis will move towards the curvature. Okay. So, we can also put a note, M is applied such that radius is closed. We have decreased the curvature. Now, let us write down the equation for strain. Strain epsilon is y plus E delta d phi change in length by original length. Okay, see here, original length is r plus y d phi, change in length is this. So, I have written a strain equation, call this equation as 3. Okay. Let us assume that longitudinal fibers do not elongate. We are only talking about the cross section. So, I can write stress as E into del d phi by d phi of y plus E by r plus y. Can I write this? Equation 4. Okay. Let us see the nature of the stress. I want to copy this figure. Let me project this extrudas point and intradas point and the neutral axis point at any specific reference frame. The reference frame may not be at the center. Okay. There is a reference frame. It need not be at the center, it can be anywhere. I am just putting the point. Okay. So, for your convenience, if you really want, we can also do it the other way. Let us rub this. Let us put the reference frame somewhere here. And let us project this, okay, for our convenience. So, this is my neutral axis. So, let me draw the figure. Now, we know this is going to be tensile, this is going to be compressive, and the stress is going to be non-linear. So, this is tensile, this is compressive, and this variation will be hyperbolic, it is non-linear. And let us, for our understanding, we already know that this is the convex side, which is extradas, and this is the concave side, which is intradas. M is applied in a specific style. Okay. This is the stress variation and the stress intensity at any distance y, at any distance y is given by this equation, and this is non-linear. Okay. Now, let us say for equilibrium condition, total compressive force should be identically equal to the total tensile force. Now, since the average stress on the concave side, okay, on the concave side is more than the convex side, neutral axis shifts towards the center of curvature. Okay. So, stress dA for the area A should be 0, equation 5. Let us substitute equation 4, this is the equation 4 in 5. So, substituting equation 4 in equation 5, we get, what is equation 5? Okay. So, integral E d phi by d phi y plus E plus R plus y dA should be set to 0, correct? Which means E d phi by d phi integral y plus E by R plus y of dA should be set to 0. We call this equation number 6. Now, friends, since E d phi by d phi cannot be set to 0 and this is a constant quantity, I must, so one should accept that integral y plus E by R plus y dA should be only set to 0, equation 7. So, let us impose this condition now. Now, I split this integral into two parts. This integral can be split into two parts as y by R plus y dA plus E times of 1 by R plus y dA is set to 0, equation 7a. So, I call this as integral I1 and integral I2. Okay. Let us pick up I1. I1 is integral y by R plus y of dA. This integral has the dimension of area, because this is over the area A. So, I could say now this is identically equal to MA, where M is a constant. This depends on the shape of the cross section. The quantity MA is called modified area of cross section. Why modified? The original area got modified because of application of M in a specific style, that is M is closing the curvature. Okay friends. So, we have got a very interesting integral that y by r plus y dA over the area A is identified as some factor of A, okay, which is a cross section property, depends purely on the cross section. So, M should be arrived now for various possible cross sections that can be used in curved beams. That is a geometric property. Okay, we will do that. We will do some illustrative examples to work out M for different cross sections. Having said this, now let us look into the second integral. Second integral I2 was given by E times of 1 by r plus y dA for the area A, which is now equal to E times of r plus y minus y by r times of 1 by r plus y dA. Can I write like this? Okay, of the area, which can be said as E by r plus y by r plus y dA integral A minus y by r plus y dA over A. Friends, if you recollect, turn back your notes, this particular term is known. What is this term? You know, this is actually equal to MA, right? See? So, can I now write this as E by R A minus E by R MA? Can I write like this? This is my I2, integral 2. Am I right? So, I have both the integrals now. Integral 1 I have, this integral 1, which is simply MA, and integral 2 also I have. Now, can I substitute and write equation 7 again? What is 7 equation? Can I write equation 7 again? Let us rewrite. I will copy these equations better. Okay. Selection 2. Now, substituting for integral I1 and integral I2, 7a now becomes MA plus E times of I2 is actually this value, A by R minus E MA by R. Am I right? E MA by R, which is now set to 0. That is what we want, isn't it? Set to 0. So, if you do that, I can cancel this. Now, I can write M plus E by R minus EM by R is 0. Friends, please note, M in the above equation does not represent the moment. Please understand, it is a common confusion. Does not represent the moment. It represents or refers to modified area. very, very important. Okay. So, we have derived this equation, closed form. I hope there is no confusion in this. Let us go ahead. Having said this, let us say now m is equal to, see here, m is equal to, let us rewrite this equation, or I can straight away say m is equal to E times of m by r minus 1 by r. Can I say that? Simplifying. So, m is equal to E by r of m minus 1 or E, which is the shift of neutral axis from the centroidal axis given by m by m minus 1 of r, equation 8. That is a very interesting relationship we have. If I know the modified sectional area, if I know the radius of curvature of the beam, I can always find what is the shift of neutral axis. Friends, it is very interesting. Now, the shift of neutral axis also becomes part of the geometric property, whereas m is a modified area. Okay? M is a modified area or modification in the area because of capital M applied on the curved beam, and E has also now become a geometric property. Okay? Having said this, further m plus E by r minus Em by r is 0. We have this equation no? Here, just see, same equation I am writing, m plus E by r, same equation I have rewritten. So, now we can also say m 1 minus E by r is equal to minus E by r. So, m can also be said as minus E by r by 1 minus E by r. Can I say this? Okay, which can be said as minus of E by r minus E by r. So, therefore, I will get m as minus of E by r minus E, equation 9. This is another form to find m or to find E. Okay? This is another form of equation. Okay. Having said this, let us move forward. To work out the stresses. Okay. So, I will draw the figure again. Let us say we have this cross section with us. I will draw, I will copy this figure. Okay. For this figure, let me plot the stress distribution. This is my reference plane. And the neutral axis. So, I should say this is my stress distribution. Okay, and let us also mark this is convex side, this is concave side. Okay, that is what we also marked earlier. The bottom is concave side, the upper is convex side or extras and intras. We have marked the same thing here again. Okay, let us now write the equation which we just now derived. Stress is given by E times of delta d phi by d phi of y plus E by y plus R. This is what we already wrote. Let me call this number of equation as 4. Let me mark it here as 4. I am marking here as 4 because the same equation is rewritten. We also have E as m by m minus 1 of R. I think this equation was 8. Let me mark this equation as 8. M is also now given by minus of E by R minus E, which is equation 9. Okay, the stress distribution looks like this and is subjected to a moment such that the curvature is decreased. Okay, that we have to remember very clearly. So, now the cross section undergoes a non-linear stress distribution which is hyperbolic. Now, the applied moment m should be equal to the resisting moment so we say over area A into y should be equal to m. We call equation number 10. So, now let us substitute equation 4 in equation 10. We get equation 4 is here, just wrote it for you. So, now m becomes E del d phi by d phi integral y plus E r plus y dA, y dA. Am I right? Just check this equation 4 and I have an y here, y d. We call this equation number 11, which can be now written as E times of del d phi by d phi integral y square plus y e by r plus y of dA. We will call this equation 11a. Okay. So, we call this as integral I. Now, the integral I is integral y square plus y e by r plus y dA over the area E, which is identically split into two parts, integral y square dA by r plus y or a plus E times of y by r plus y dA over E. We call this integral as I1, this integral as I2, where I1 is integral y square dA by r plus y for the area A, which is y minus Ry by R plus y of dA over A is check. Okay, this is equivalent, is it not? So, I1 now becomes integral y dA for A minus R times of y by R plus y dA. I1 is further split. Okay. So, friends, we will continue this discussion in the next lecture. I want you to evaluate this integral. So, I leave a small homework. So, in this lecture, we extended to learn curved beams with large initial curvature. We are in the process of finding out the equation to obtain the stress and its distribution across the section of a curved beam under large initial curvature. There is a small homework given to you. Evaluate the integral I. Okay, we will discuss it in the next lecture. Thank you very much and have a good day.